All right, in the last class, we have learned how to discretize equations using the 4-time central space scheme. Today, we're going to implement it on heat equation. This is heat equation. Partial U, partial T equals alpha del squared del x squared. It's in 1D. We are going to have a rod of length from 0 to L and time greater than 0. U is the temperature. We want the temperature at the ends. From the left, we want the temperature to be 0. From the right, we want the temperature to be 0. And initial conditions, we want at t equals to 0, at time t equals 0, we want a sinusoidal behavior on the rod. And we already have seen how these schemes have how to discretize the scheme for the time we go forward and for the space we go central. And we already have seen how the recursive relation becomes, and this lambda is defined this way because you have del t coming up and del x squared is down, and the alpha will be multiplying because it's somewhere here. We already have seen this in the notes. Now, for stability, we know that lambda has to be less than a half. So what do? We have two options. You manipulate the length and the time until you achieve this, or you can simply set this to a half and solve for t to find the delta t that would get this to a half automatically. So when you solve it like this, you get delta t should be less than or equals to that. So in solving for dt, you should get 0.5 as lambda if you use this dt. So then lambda should be 0.5. But then we don't want 0.5 because that is the maximum you don't want to reach for stability. So you can multiply it by some you can use the 90% of this or maybe 95% of this, but just make sure that you don't use exactly how it's supposed, because it will blow. This is the analytical solution. We are going to compare our solutions with this one after implementing the finite difference schemes. For the discretization, dx, that's the increment in x, would be L over n minus 1. Why n minus 1? Because if you have 10 points, you will have 9 intervals. If you have 5 points, you will have 4 intervals. So we are looking at because dx is the number of intervals. And that's why you have n minus 1. For dt is dt over n. You don't have any headache. For lambda, it's defined this way. And for stability, lambda should be less than 5. This is just the decay rate. Now, here we begin the implementation. You import NumPy for numerical operations and matplotlib for plotting. What is the length of the domain? Let's make it 10 meters. What is the time? Let's look at 10 seconds total time. What would be the diffusivity? That's alpha. Let's make it 0.4. How many increments do you want to discretize the time? Let's assume we want 5 time steps. So 0, 1, 2, 3, 4, 5, and that's it. How about, oh no, that's for the space. So for the space, let's make it 100. Let's have 100. And for the time, let's make it 5 for simplicity. Shift enter, we run this code. We move to the next. Here, dx, like we said, is L over nx minus 1. And so that now we can make x as np.lin space from 0 to L in steps of nx. Oh, no, sorry. 0 to nx in steps of to L in steps of dx. It's not happy. Why? Oh yes. Linspace would take the left limit, the right limit, and then the divisions. So we want to divide it by 100, so it has to be in nx. And this one, the t is simply okay. So here you have two options. Let's look at this, t over nt, and let's look at what lambda would give. You remember lambda? So I just said this one a little while ago. You remember that lambda is alpha times dt by dx squared. So let's look at the lambda we would get if we did this t over nt. We're going to get a big lambda, 78. So if you want lambda to be less than half, you have two options. You can go here, change the length to 100. And then you have like 0.7. 0.7, it's still big. So you may want to make it 110. And then you have 0.6. You get the idea. Or you can leave this guy as it is, 10, for example. Yeah, let's make it 10. You can use this formula, this one, dx squared over 2 alpha. So instead of having to maneuver, you can make this dx squared over 2 alpha. In this regard, you will have 0.5, but we don't want 0.5. It has to be less than that. So you multiply this by 0.9. That's 90% off. Now you have 0.45, and now you're good. Next, we move to initial condition. Initial condition is supposed to be sine pi x over L. So np dot sine np dot pi times x over L. That's initial condition. In the left, we say we don't want any temperature. In the right, we say we don't want any temperature, so there will be zeros. You run this cell, and then you initialize where you want to store the results. So we want to store the results in a variable called results, and we need to first store the initial condition. So let's store the initial condition, u of 0. You run this. Now, we want to begin the implementation of the finite difference scheme on the heat equation. Like we already have explained in this recursive scheme, you want to, at every time n, you want to loop through j's. For example, if you heat in the rod, when you heat it, after 5 seconds, you come back, you see the condition of the rod after 10 seconds, but at each time you come back, you're going to see the full rod. So at n, you are going to loop through all the j's, because j is for the x, as you can see. So we're going to run through time, but for each time increment, run through all of the space. That's what we're going to do. And therefore, but first we have to be careful. You have to be careful because we first have to start with the initial condition and then update, right? Because when you start with the rod, you heat it. When you come back at some later time, you should see the status at that later time, not some initial condition again. So we want to say you current u. Let's call this current u. Current u equals u0 dot copy. This is the current u. Now we look for I in range NT. So we have new U. So we will have a new U, which will copy. So is current U, U dot copy. So this new U will copy the current U. Let me copy this current U, Control C. And then we'll operate with it. So now you can say, new U. Oh no, now you can look through the space. So we can go for J in range. Here you have to be very careful because you are going to leave the two ends empty. So for the left end, we will start from 1. We are skipping 0, and then n minus 1. Nx minus 1, sorry. This is really crucial. Why nx minus 1? First, why 1? Because the leftmost end is supposed to be 0. And we know that Python counts from 0 to, it doesn't reach the last one when you are in range. So nx minus 1 is the last one. But when you want this range, when it counts, it will count from 1, 2, 3, 4, but it will never reach this. It will stop from the last one next to this one. And therefore, we want this empty and 0 empty, and that's why we have here 1 and nx minus 1. It's really important. Let me show you something. Let's say range 1 to 10. You're going to, okay, so I in range 1 to 10. Let's make some short. Yeah, what you see is it will start from 1 and stop at 9. That's what I'm trying to say here. So that means the 0 is empty and the 10th one is empty. And that's exactly what we do here. This is very important for the boundary condition. Then we loop. So new U of J equals the normal recursive formula. So it's going to be this guy, current U of J plus lambda times current U of J plus 1 minus 2 times current U of J, minus 2 times current U of J plus current U of J plus 1. Now you have this done. You have the algorithm done. You have this implemented. Where is it? Yeah, you have this implemented. Uj plus lambda. Oh, it's plus lambda. I hope I didn't miss anything. Yeah, plus lambda. Anyways, we're done with this. Now we set the boundary conditions. You go out of the loop. You get new U of 0. So I can here say set boundary conditions. Now here you can say getting initial condition. Here you can say starting with initial condition. And in the beginning, it starts with this. But as time goes on, it will update. How does it update? First, let's set the boundary condition. New U of 0 equals 0. That's the Dirichlet boundary condition. Because the Dirichlet boundary condition, you know the values at the boundaries. New U of minus 1 equals 0. You have set the boundary conditions. So now you want to update, because in this loop, when this finishes, new u has changed form. And this guy would want to always copy the current new. So what do? We say before you get out the loop of the loop, the current loop, current u equals new u dot copy. Because new u has changed here. And this guy, when we come here, is looking for current u. If you did not add this, it will go back and use the initial condition. So you have to update. So here you can say updating the state of the rod before the next time iteration. Finally, you have to also get the results to capture this. So results dot append new u dot copy. And then you're good now. So you run this code and you're done. Finally, you have to, you can, or sometimes you can ignore it. But anyways, you can say results equals np.array results. What did you do here? You to numpy array. That's what you did. And then you want to plot. But first, we would like to write the analytical solution. But first, let's visualize first. So plt.figure. Let's give figure size. I like to always customize the figure size before I plot, but it's not necessary. Equals. I like 15 by 4 because it will give me the chance to see everything without having to scroll. So plt.plot. I want to plot the initial condition x, comma, results of 0. I think because we have, let's see, we can even plot all of them. Let me see. What was the time steps dt? Nt is 5, but dt will make it longer because dt has been compromised by this. So now, okay, anyways, let's plot results of 0. Let's make it red, dot, dot. So it becomes a dashy red. Label equals u of x, comma, 0. Let's plot this and see. Okay, that's what we got. That's the initial condition. Now, let's plot also the final condition. U of L. So that means you're looking at U of -1. The final. Oh yeah, so let's make this blue. And what do we want to do? We want to see the names come out. So plt.legend. Good. And let's now see if we can, okay, let's give it the xy name plt.x label. This is X. So plt dot y label, that is Y. And yeah, so that's Y dot X. You can give it the title, plt dot title, plt title, forward time central space solution to 1D with the equation. All right, now let's add the analytical solution to this. Let's add the analytical solution. Let's say current time is nt times dt. That's the final time, right? What happened? Oh no. Yeah, the name in current time is nt dt. And let's say analytical solution equals, I think we have it here. It's sine pi x by L exponential minus alpha times pi by L squared t. So np dot sine np dot pi times x over L times np dot exp minus alpha times something, that's the 2 times t. Here is np dot pi by L. But the t is not t, we call it current time. Current time we run. Now we would like to plot anal as well in this. Control C. Okay, so I missed here. This is not L. This is T, like the final time, right? Okay, T final. That's how I'm supposed to write it, not L. Anyways, let's run it first. Now let's copy this. I want to add the analytical solution in this. Control V. It's called T analytical. I want to call it U of X T analytical. Analytical. Let's make this star. And maybe this one can be black. Good. What we see here is the initial condition and the final condition. And when we compare with the analytical, it is correct. What can you do more? You can add source term. For example, you can add some source term in this algorithm to solve a real heat equation. You can convert it to 2D or 3D. In this case, you loop through J and then you loop through K. Anyways, I think we can stop here regarding this.